Hello, everyone. Hello. Yes, so once again, apologies for the delay in publishing the assignment, but you can see the draft assignments here. The maths will be published today, so if you are starting today, don't start maths from here, but do have a look at the physics side of things. Okay, so let's dig into some physics. So the topic is machines. And well, machines are designed to make our life easier, right? They're designed to give us an advantage. And when we're talking about mechanical, well, we're going to talk about machines, we're talking about mechanical advantage. Okay. So what does that mean? Well, if you take a simple scenario, fit balancing act. Okay. Okay, so if, let's say you have something heavy. You have an 80-kilogram human, and you can lift that human using probably a 10-kilogram mass. Nope. Okay, a 15-kilogram mass. Nope. A 20-kilogram. So basically, if you want to lift a human, you can use a much smaller force. So if we take a picture. Take a picture. So here, what we have here is an example of a mechanical advantage. The force needed to lift a human is 800 newtons. That's the force lifting the human. And the force that we are pushing here is only 200 newtons. 200 newtons. So using a force of 200 newtons, we can lift 800 newtons. So mechanical advantage. In this case is times 4. Does that make sense? Did you learn something new, or did you already know this before? Not new. Yeah, that's fine. There are different types of machines. Different types of machines that we use, and they all give us a mechanical advantage. So, problem 1. Could Archimedes move the earth? So Archimedes famously said that give me a place to stand on and give me a lever and I can move the earth. So effectively, he said that if this is the pivot, we can assume that we live on a bigger planet, but surprisingly same gravity as on Earth. Yeah, imagine we live on a much bigger planet. and there's a very long lever. Let's call it L2, and this is L1. Yeah, imagine an infinitely strong plank and then in the fulcrum. Let's say for simplicity that this is 1 meter. Oh, actually, no, we don't need to imagine that this is 1 meter. But what we need to understand is the proportionality effect. So theoretically, yes, with any force you could move any other object. But what you need to understand, if you take a plank proportionally, let's say that this is 1 meter and this is 10 meters. If this end moves by 10 by 20 centimeters, for example, this end would only move by about 2 centimeters. Not exactly 2, but roughly 2. Actually, no, exactly 2. Exactly 2 centimeters. Sorry, I'm saying weird things. No, it's exactly 2. Okay. And this is an intuitive understanding. You can prove it if you wish. So the first thing that we need to understand that L2 to L1, the ratio of L2 to L1 has to be the same as the force that you apply, or the force 1. This is F1, and this is F2. Sorry, the F1 is the force required to lift the Earth, and F2 is the effort, F2. So the ratio of the lengths has to be the same as the ratio of masses. But also, it is the same as the ratio of the distance moved. So let's say Archimedes moves a distance x2. This is the distance moved by Archimedes. And x1 is the distance moved by the Earth. And it's going to be x2 over x1, the ratio of the movements. Okay. Now, we need to find that ratio. The force, the mass of the Earth is about 6 times 10 to the 24. That means the force needed to lift the Earth is mass times the gravitational field. We're assuming that the gravitational field is 10 newtons per kilogram. And the force of Archimedes, well, let's take a reasonable force. How much force can you apply? Well, I'd say about 500 newtons for a strong human. It's about 500 newtons that Archimedes can hold. So F2 is 500 newtons. That's an assumption. The mass of the Earth, so it's going to be 6 times 10 to the 24 times 10 divided by 500. What do we get? We get times 212, boom, 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 3, 60 over 5, 22, 60, 12 times 1.2 times 10 to the 23. That is the ratio. Now, Let's write it down. The weight of Earth is 1.2 times 10 to the 23 times greater than the force of a human. Hence, Archimedes will have to move 1.2 times 10 to the 23 times further than the Earth. So then let's define what does it mean to move the Earth, right? What does it actually mean? I would say at least a meter. If you move the Earth by 1 meter, that's reasonable. Okay, maybe 1,000 times less. Doesn't really make a difference. Well, okay, let's take to move 1 meter. Archimedes will have to move 1.2 times 10 to the 23 meters. Okay, so that's getting interesting. So in order to move the Earth by only 1 meter, you would need to move 6 times or 1.2 times 10 to the 23 meters. And that seems like a lot. How fast can you move? Well, it will take at a speed at, let's say, if you move 10 meters per second, which is a very reasonable speed, it will take 1.2 times 10 to the 22 seconds, which is that's a scary big number. 1.2 times 10 to the power 27 divided by 365 divided by 86,400. It will take him like 3.8 times 10 to the 19 years, which is slightly more than a lifetime. That's more than the age of the universe. It's 10 billion times the age of the universe. So answer is no, you wouldn't be able to move the Earth. You wouldn't be able to move the Earth any visible amount, even if all his life he was pushing. Okay, and even if he was traveling at the speed of light, even at the speed of light, it would still take him billions of years. About 10 million years. About 10 million years. So no. Okay. So he was wrong about this. Anyways, problem 2. Discuss how a hydraulic system works and how energy is conserved. Well, this is a simple example. This gets slightly confusing. That in a hydraulic system, because we tend to say that pressure 1 is equal to pressure 2, and that's assuming that the pistons are in the same depth. But we don't really need to worry about that too much. We just can say that pressure 1 in the liquid is equal to pressure 2 in the liquid, because that's how it works. If you've ever seen, so pressure is the same in all directions. That's Pascal's law. Pressure in a fluid is the same in all directions. Okay. This Pascal's law does not take into account the change in depth. And as you go deeper, the pressure increases. But we are talking about very small differences in height. So we ignore when we do hydraulic systems. In hydraulic systems, let's write it here. In hydraulic systems, you usually ignore the change in height. So, yeah. So how does that work? Well, let's say you have two pistons, a smaller piston and a larger piston. If you push on the smaller piston, that pushes the liquid into that container, and that piston rises. Makes perfect sense, right? The force applied to this piston gets multiplied depending on the area of the pistons. So the force F1 is equal to pressure times the area. Is P1 times A1. And the force on this piston, F2, is equal to P2 multiplied by A2. Okay. And if you divide them together, so F2 divided by F1, to divide the second by the first one, it's going to be P2A2 divided by A1, sorry. But P1 is equal to P2. We already know this because the pressure in a liquid is the same everywhere. Again, ignoring the change in depth. And so F2 divided by F1 is equal to A2 divided by A1. So if this area, for example, was 200 centimeters squared, and this area was 800 centimeters squared, and this force was 10 newtons, this force would be 14 newtons. So the mechanical advantage in this case would be 4. You are increasing the force. And this is a very commonly used thing. So hydraulic what can we do? Hydraulic jack. Lovely. So this is a hydraulic jack. Let's have a look. So what it does, it goes underneath the car. And so the car goes here, a part of the car. So this is the wheel. This is the wheel. So suppose you want to change a wheel. You put this underneath your car. Check. like this. And use it to lift the car, take off the wheel, put a new wheel, pop a new wheel back on, and drive away safely. And you can see that it has a piston. It has a small piston here with a small area, piston of area A1, and another piston of area A2. And the amount of force that you apply here, so you have a handle which sticks into here, and you move the handle repeatedly, and that pushes this small part. This pushes a small part in, and then the liquid pushes the bigger piston out. And the ratio of the forces, the force that you need to apply here, F1, and the force generated here, F2, F2 to F1 is equal to A2 to A1. So if the piston is, let's say, 10 times bigger, then the force is 10 times bigger. All right, and this quite an ingenious thing. Now, let's suppose the smaller piston moves down by x1 centimeters. Moves down by x1 centimeters. And so the bigger piston will move up by x2 centimeters. X2, no, doesn't have to be centimeters, x2 meters, right? Now, how do you work out? Well, this pushes this volume of water, of liquid, doesn't have to be, it's not water, usually not water, usually some kind of oil. So this amount of liquid is displaced. The volume is equal to, well, it's a cylinder. That means it's the height times the area, A times height. So it's going to be A1 multiplied by X1. So the volume of the liquid that is pushed down through the pipe is A1 times X1. And the volume of the water here, of the liquid here, this is the additional liquid on top. It has to be the same volume. Volume is equal to A2 multiplied by X2. But because it's the same liquid, the liquid doesn't escape. Volume 1 equals volume 2. Volume 1 equals to volume 2. And that means that A1 X1 is equal to A2 X2. And we can work out X2 from here. X2 is A1 X1 divided by A2. That is the distance moved by the second piston. And as you can see, it's smaller than the distance moved by the first piston. Now let's talk about work done. Work done by the pistons. So work done by the first piston is the force times the distance. And work done by the second piston is F1, F2 multiplied by X2. They have a very different force. Well, let's express the force F2. F2 can be expressed as F1 multiplied by A2, A1. And we already know that x2 can be expressed as a1 times x2. So we can simplify this. We can take this and take this and plug it into here. So the work done by the second piston is F2, and we already know that F2 is F1 times A2A1. So F1 multiplied by A2 over A1 multiplied by X2, and X2 is A1X1, A1X1 divided by A2. And what do you see? A1 cancels, is F1X1. It's the same as the work done by the first piston. Does that make sense? Is that making sense? So you're using a smaller force to get a bigger force, but this piston moves less than this piston. And even though you have a much larger force, the amount of energy or work that is transferred is the same. So you win in force, but you don't win in energy. So conclusion. Same. Increases force. This is force, but the work is the same. Right. So basically, you need to move the handle much further. You move the handle through a large distance in order to move the car just a little bit. So hydraulic using a hydraulic jack to lift a car. Doesn't really show. Okay. Not really useful. But anyways, you understand you need to move the handle a lot. Okay, I won't stop here. Okay. Another force multiplier is a ramp. You might have seen ramps being used to lift heavy things. The first example that comes to mind somehow is the construction of pyramids, although I don't think anyone knows exactly how they were built, but we have a rough idea. So using ramps, to move blocks, and not very useful. Images. Oh yeah. So this is the picture that came to mind. Right. So a ramp is it was used to lift heavy blocks onto the pyramid. So how is it a force multiplier? Well, let's have a look. Let's go a little let's do a little bit maths. Let's be a little bit mathematical about it. So let's say we have a ramp and a block, and And let's say for simplicity, there's no friction. No friction. Well, what are the forces on the ramp? Well, there's the gravity, mg. There's the normal reaction force. And that's it. Well, we need to push it. F is the force of pushing. And the push, in order to, for it to move at constant speed, so we need to break down mg into components. And you already know how to do this. This is mg cos theta, and this is mg sine theta. In order to move at constant speed, F has to be equal to mg sine theta. Yeah, does that make sense? No questions here? So the force that we push has to be equal to that force. That is the component of gravity that pulls the block down. All right. Your aim is to get the block from the bottom to the top. Your aim is to get the block from here to here, from the ground to the top. And if you were lifting it, you would need mg. Easy, right? Because to lift something, you need to apply a force which is exactly mg. But here, it's mg times sine theta. And we know that sine theta is always less than 1. Well, less than or equal to 1. And that means that mg sine theta is always less than mg. So the force, yeah. If you were lifting it, you would need a force equal to mg. But because you're lifting it along a ramp, you only need mg sine theta, which is always less than mg. Does that make sense? Any questions? I'd love to answer the questions if you have. Okay. The up bit. What do you mean by up? So this is the pyramid. You want the block. Oh, arrow going up on the block. That's mg. That's not. That's supposed to be mg, not up. Mg. If you wanted to lift a block just vertically from the bottom to the top, you need a force which is mg. But if you want to lift it along the ramp, so lift the block without a ramp, the force is equal to mg. Lift the block with a ramp, F is equal to mg sine theta, which is always less than mg, less than or equal to. Well, you can always balance. You can always balance, yeah. regardless, you need to be able to move the block along a horizontal line. So if you can move it along a horizontal line, then you can just, yes, use a shallow ramp. If the block is so heavy that you can't move it at all, then a ramp is useless. If you can always find the angle at which you can still move it, and you still have a mechanical advantage. Okay. Yes, the friction. Yes, there's always going to be some friction, and the friction is mu mg cos theta, which is yeah, which is not pleasant, but so as long as you, yeah. Okay. Anyways, now let's. And even though you increase the force is increased. Well, as in you need less force to move it, but that means you've increased your own force. You can use 100 Newton force to lift 1,000 Newton block. Yeah. Example. 100 Newtons force can lift a 1,000 Newton block. For example. That's why it's a force multiplier. So a ramp is a force multiplier. But we win in the force, but we lose in distance. Yeah, we have to move a longer distance. And let's see how much longer. Let's say we have a ramp and it has an angle. Now, and the height of the ramp is h, and the length of the ramp is L, and the angle is alpha. How much work do you need to do if you want to lift a block from the bottom to the top directly? How much work? Can somebody help me with that? Lifting a block directly is the force times the distance moved. Yes, so work done is the force times the distance moved. And the force is mg, and the distance is h multiplied by h, so it's mgh. Unsurprisingly, the distance you need to move is mgh. Okay. Sorry, not the distance. The work you need to do is mgh. But what if you move the block along this line? We already know that the force here, the force is mg. Here, the force is mg sine theta. Work done, so vertically. And now work done along ramp. It's the force times distance. So the force is mg sine theta. And the distance is L. But we know that sine alpha, so sine theta is h over, okay, sorry. This is theta. We know times that sine theta is h over L. It's the opposite over hypotenuse. And that means that L is h over sine theta. So it's mg sine theta multiplied by h over sine theta. And surprise, surprise, the work done is mgh as well. So with no friction, the work done along the ramp is still mgh. You use a smaller force, but for a longer distance, and it turns out that the work you do in both cases is mgh. So once again, you win in force, you lose in distance. The work stays this. The work done is the same. Okay. Any questions? So work done if you move it vertically, and work done if you move it along the ramp is also mgh. Okay. Gears. Gears is the next thing. Gears are fairly straightforward. If you've ever ridden a bicycle with gears, you know that if you want to go fast, you need so bicycle gears. Bicycle gears. Okay. So if you want a lot of force, then you choose a low gear that allows you to travel up steep hills. And if you choose a high gear, you can go fast, but you need more force. You need to apply more force. So yeah, basically the gear ratio, you always have the primary gear. This is the primary, and the secondary. Primary is sometimes called the driver, and the secondary is, oh, I forgot the word, is driven. Anyways, the primary or the driver, second, driven gear. So gear ratio is the number of teeth on is it secondary? You get more. This is an engineering thing. Depends on gear ratio, driven or driver. Driven divided by driver. Yes. So the number of teeth on secondary. Divided by the number of teeth on primary. So if ratio is greater than 1, that means it is a force multiplier. And if the ratio is less than 1, it is a speed multiplier. In the case of a bicycle, of a force multiplier is that when you want to go slowly up a steep hill, and this is when you go fast with when you go fast on a level road. Level road. Okay, so let's have a look. Here we have a okay, so here we have a gearing system. All right, so this is the driver, and this is the driven gear. And as you can see, because there are fewer teeth on the driver spins faster than the driven gear. So you would use this setup when you want to go up a hill, but you can change that. So number of teeth on the primary, let's say it's 30, and this is 20. So now you can see that this goes slower than this one. And indeed, it is, the ratio is 1.5, well, 1.5 to 1. Okay. So you have yeah, so the driver and the driven gear. So hopefully, I mean, it's kind of intuitive. So let's take a gear. This is a gear with 13 teeth. So let's decrease the number of teeth. Let's make it 10 tooth gear. Let's make add another one. And if it has 20, say it has 20. And you can see that this small gear runs at 6 RPM, rotations per minute, 6 rotations per minute. And the big gear rotates at 3 rotations per minute. Okay, and because the ratio of the speed of rotation, in this case the angular speed, because we are interested in how many rotations per minute, and yeah. So let's have a look. Just go this. So this is the driver, and this is the driven gear. So this is 10 teeth. This is 20 teeth. And this is 6 RPM. And this is 3 RPM. And again, if you think about the work done, then yeah, if you think about the work done, then it's going to be the same. Let's show that. Let's go slightly deeper into this. So if you have the radius R1 and the radius R2, you see that there's a contact. There's a contact force in here. This contact force pushes the little gear down, the top gear up. So and the force is the same, F and F. And this is R2. So we know that the moment of a force is force times distance. So in this case, the force F1 is equal to, sorry, moment of the force on this gear is equal to F1 multiplied by R1. And the moment of the force on the second gear is F2 multiplied by R2. And because we know that F1 F1 is equal to F2 because there's a contact. It's a contact force. Newton's third law tells us it's the same force. If one gear is pushing one with a force F1, the other one is pushing with an equal but opposite force. And therefore, you can have F1, you can express F1 as M1 over M1. M1 over R1 is equal to M2 over R2. And this means that M2 over M1 is R2 over R1. What that tells us is that the bigger gear has bigger moment or torque. Yeah, so generates a larger torque. So it's a force multiplier in a way. Even though the force is the same, we still refer to it as a force multiplier, as in a moment multiplier. It increases the turning effect, right? Basically what it means, if you were trying to hold the gear, it would be easier to hold the little gear with your hands rather than the big gear, because the big gear will have a oh no, sorry. I'm saying rubbish. No, sorry. The force is the same, of course. The moment, if you were trying to hold it at the center with a spanner, for example, then it. But let's not go there. Let's not go that far. Design gearing for an analog clock. So it's gear generator. So for an analog clock, well, we know that an analog clock, so we have the second arrow, we have the minute arrow, and the hour arrow. So if you want this, so let's say this is, let's reduce this to 40th. 40th is the smallest number we can get. And the RPM is 1 rotation per minute. So that's obviously the second arrow. Right, so this gear, if you're thinking about a clock, analog clock gears, so clock gears. Okay. So well, it's very interesting to investigate. You just need to count the teeth. All right, so I'm not going to do that, but you can do that. You can later count the teeth. But what I need to do is I need 3 different wheels rotating at 3 different speeds. So this represents the second arrow of the clock. So it goes around every minute. So that means 1 RPM, literally. That's what it means, 1 RPM, 1 rotation per minute. I'm going to add another gear. And I want it to go 60 times slower. That means 1 rotation per 60 minutes. So I need a gear ratio of 60. So I could use a gear with, if this has 4 teeth, I would need 60 times 240. I don't think that's even possible. 40. All right. Yes, it is possible. Slightly bigger. So that's not how we do it. If we want a bigger gear ratio, we use several gears. so let's make it 4. So how do you make 60? 60, you can make 60 by 2, okay, 15 and 4. So this would be 60. Can we make 60? 60 is still too big. Okay, 30. 30. Okay, that's fair enough. We have 30. 30 teeth. So if this goes at 1 RPM, this goes at 0.13 RPM. And we want to add a new one. And let's make it make an axon connection. And reduce the number of teeth to 4. And then add another gear with, so we had 30, so that's 15 times 2, 8. Let's make 24. All right. So I think we've done it. So this gear, the first gear, is 1 rotation per minute. This is 30. Oh no, sorry. It is 30. That doesn't even divide. 15. So the ratio is 7.5. 7.5 to 1. And then we go back to 40. Okay, let's check. If this is 60. Yeah, that doesn't make sense. It doesn't work. Okay, so let's make this 15. So 7.5. This 28. That doesn't make sense. We need 7. We don't need 7. We need 5. 20. Go to 5. Then we need 6. So the second is 2 and 2. So 4. We've got 5. 12 and 4. So 4. So that's going to be 5. Okay, and so that drops what? 4 to 20. That's a ratio of 5. 5 to 1. RPM. Sorry. 24. Okay, add new gear. Axon connection. Reduce that to 12. Okay, that worked. Sorry, confused myself in the ratios. So now you can see that if the driven gear is 60, that if this rotates 60 times per minute, this rotates exactly 1 times per minute, and then you can keep building to make. So this would be the second the second arrow, the second minute hand of the clock. Second hand of the clock. This is the minute hand of the clock. So we'll reduce that to 1. You can see this makes a rotation in 1 minute. This will make a single rotation in 1 hour. So you can see it's really, really slow, 60 times slower. And then you do a similar system. So you can play around. It's called geargenerator.com. So do play around with it. Okay, let's move on. A moment of a force, and this is crucial. We need we're getting very mathsy at the moment. And a moment of a force is force times the distance, the perpendicular distance to the pivot. So moment of a force. Moment is force times perpendicular distance to the pivot. That's important. So we have a pivot and there's a force. So all we need is force times the perpendicular distance. So this exercise is very straightforward. So it's force times the perpendicular distance through it. So 3 times 2 is 6 Newton meters. Now, a moment is a vector quantity, so it's clockwise. In this case, it's going that way. It's trying to rotate around the pivot that way. So 7 times 1.5, 10.5 Newton meters clockwise. Now here, this is the pivot, so this is rotating anti-clockwise, so it's 13 Newton meters counterclockwise. Now, what about 4? What's the moment of the force in question 4? That's fine, Mark. The moment is 0 because the distance from the pivot is 0. So the force goes through the pivot. So this is 0 Newton meters. The moment of the force is 0. Here. Now, this is the pivot, and it's force times perpendicular distance to the pivot. This is 5 meters, but we need the perpendicular distance to the pivot. Okay, and let's call it h. So h is equal to 5 multiplied by sine 30, which incidentally 5 times 0.5, which is 2.5 meters, and times the force. So the moment is force times the perpendicular distance. So it's 4 multiplied by 2.5, which is 10 Newton meters. It's 10 Newton meters counterclockwise. And here we need to find this distance, the perpendicular distance. So the distance, this is 140, so this is 40 degrees. And this distance is 5 times sine 40. So the moment is 3.6 multiplied by 5 sine 40 Newton meters. So it's something 3.5 times. So that's 3.6 times 5, 18 times sine 40. This would be approximately 11.6 Newton meters clockwise. Right. Here we need to find the total moment around point P. So there's a pivot at P, and we're pushing. So this force is pushing clockwise, and this force is pushing anti-clockwise. We need to find the total moment around point P. So moment, there's a force pushing anti-clockwise and a force pushing clockwise. So in A, the moment total is equal to 3 times 1, the force times distance, 3 times 1, minus 2 times 4, minus 2 times 4, because the distance is 4 meters, and you're applying a force of 2. So it's 3 minus 8, which is minus 5 Newton meters, or 5 Newton meters. You can say minus 5 clockwise, or you can say it's 5 Newton meters counterclockwise. How well do you understand this question on a scale of 0 to 10? But please be honest, because I think I've been rushing a bit here. I'm happy to slow down and explain. Okay, lovely. Okay. All right. Happy to explain again. Okay. All right. The negative. Okay. A moment of a force. Moment is force times distance. But we're not just distance, it's a perpendicular distance. Perpendicular distance to the pivot. Distance to pivot. Now, here, and a moment is a vector, so it has direction. In this case, for simplicity, we say it's either clockwise or anti-clockwise. So clockwise is positive and anti-clockwise is negative. So overall, we have a positive moment of 3 times 1, which is 3, and a negative moment of 2 times 4. So let's just so moment clockwise. The clockwise moment is the moment of the clockwise force. It's with reference to the pivot, yes. With reference to the pivot, so it's 1 times 3. 1 times 3, which is 3 Newton meters. The anti-clockwise moment is equal to 2 newtons times 4 meters, because that's the distance from the pivot is 4 meters. So that's 8 Newton meters. The total is 3 minus 8, because we don't have to choose that, but I've chosen that clockwise is positive, anti-clockwise is negative. It's minus 5 Newton meters. Yeah, what about you, Vishaka? Okay, so here we have a pivot. We have a clockwise force, and an anti-clockwise force. What do I mean by clockwise force? Well, it's a force that is trying to rotate the system clockwise, and an anti-clockwise force is trying to rotate the system anti-clockwise. So the moment of that force is 3 times 1. Here is 2 times 1. And this is 4 times 3, because the total distance is 3 meters. So the total moment in this case, so clockwise is 3 times 1 minus 2 times 1 plus 4 times 3. Because this one is positive, positive, negative. Because this one is pushing clockwise, clockwise, anti-clockwise. So that's 3 minus 2 plus 12 is 13 Newton meters, and clockwise 5. Yeah. Now it's minus 5 Newton meters clockwise, so it might as well say that it is 5 Newton meters counterclockwise, which is the same thing. Because if you think about it, this force is trying, if this was the only force, this system would rotate anticlockwise. And if you only had just this force, the 3 Newton force, the system would go clockwise. They push in different directions. So the 3 Newton and the 4 Newton push in the same direction, clockwise. And the 2 Newton force pushes in the opposite direction, right? So imagine you had a clock and you're trying to rotate it. Right. In C, you have 2 forces pushing anticlockwise, so this one and this one. And you have an anticlockwise force, which is this one. Sorry, clockwise. So this is plus, this is minus, because that's the pivot, right? So you have the moment, the moment clockwise is 3 times 1, which is 3 Newton meters. The moment anticlockwise is 7 times 2 plus 4 times 2, which is 14 plus 8, which is 22 Newton meters. So the total moment is 3 minus 22, which is minus 19 Newton meters clockwise, or 19, which is the same as 19 Newton meters anticlockwise. The same idea here. Now here we have them in space, well, sort of in space. So basically we have forces like, let's say we have a plate and we have a pivot, P, and there's a force pushing that way, there's a force pushing that way, there's a force pushing that way. We want to know, will this system rotate or not? Yeah, F1, F2, F3. And we need to calculate the moment of each force, and then we can work it out. These diagram shows forces acting on a lamina, so basically a plate. In each case, find the sum of moments about point P. So we have point P, and we have forces pushing, in this case, 3 times 2 is the clockwise moment. So 3 times 2 minus 5 times 2, which is 6 minus 10, which is minus 4 Newton meters. So it's 4 Newton meters. That's the total moment. Okay. Here we have 4 times 2, which is 8. So 8 Newton meters minus 9 Newton meters, which is minus 1 Newton meter. So yeah. Here we have 6 times 4, 24, minus 2 times 7, 14, which is 10 Newton meters. Clockwise, clockwise, clockwise. Here we have 5 times 2, pushing clockwise. 5 times 2 minus 3 times 1, which is 7 Newton meters. Clockwise, of course. Now here, the same thing. You have the pivot and the distance 0.8, 0.9. So that's 0.9 times 3. So it's 2.7. Minus 0.8 times 4 minus 3.2, which is minus 0.5 Newton meters clockwise. So a moment of a force is a vector. Okay. Now here it is slightly tricky. So the clockwise is 0.8 times 5. And the anti-clockwise, now you need a perpendicular distance, remember? So it's going to be 2.5 times 6 times sine 65 degrees. And that gives us 4 minus 2.5 times 6 times minus 9.6 Newton meters. Okay. So let's do a sort of a real application. Apologies. So we have a plank AB. Plank AB has a length of 4 meters. It lies on a horizontal platform with the edge A lying on the platform and B is over the edge. Jack and Jill are experimenting with the plank. Jack has a mass of 48 and Jill has a mass of 36. If Jack stands at B, so Jack stands at B, and Jill stands at A, Jill, then the plank is balanced. Jack is 48 kilograms and Jill is 36 kilograms. This goes Jackson at B and BC is 1.8 meters. And then the plank is in equilibrium and on the point of tilting. And that means there's no force here. It's as if they are being balanced. Okay, 0.8 meters. This is, if this is 1.8, this has to be 2.2 because we know the force. And then, so we have Jill, Jack, and what's the third force? What's the third force? Anyone? There is a normal reaction from the edge, yes. Okay, so what's a fourth force? So there's a force from Jill, there's a force from Jack, there's a normal reaction here, and what's another force? The weight of the plank, of course. There's the weight of the plank, so it's the center of the plank is the weight of the plank. So there's the weight of Jack, the weight of Jill. Yeah. So now if we draw the plank, so this is the pivot, this is the weight of the plank. This is Jack. This is 480 newtons. This is Jill, which is 360 newtons. And there's a normal reaction here. Normal reaction force here, which we don't know. We could work it out potentially. So let's calculate the moments. The moments clockwise. So who's pushing clockwise? Oh, only Jack is pushing clockwise. And this is 1.8. So it's 1.8 times 480. The moment anti-clockwise is Jill, 360. So 360 times 2.2 plus the weight of the plank plus W times the distance. And if this, it's in the middle of the plank, so it's 0.2 meters, 0.2 meters. And because we know that it is on the point, okay, and the reaction force doesn't produce a moment. The reaction force is at the pivot. The distance from the pivot is therefore 0. It produces no moment. And because the plank is balanced, we know that the clockwise moment is equal to the anti-clockwise moment. And we can write that 1.8 times 480 is equal to 360 times 2.2 plus W times 0.2. And we can work out W. W is 1.8 times 480. So if it's 864 minus 360 times 2.2, 792 divided by 0.2. So 864 minus 792, 2 divided by 0.2, 360 newtons. That's the weight of the plank. Oh, so the plank is the same mass as gel. Interesting. They now alter the position of the plank in relation to the platform so that when Jill stands at B and Jack stands at the plank is again in equilibrium. Find the distance BC in that position. So they move the plank. So the pivot is somewhere here. Okay, and let's say this is X. This is 2 minus X. So this is 480. This is 360. And here is 360 again. So this is X. This is 2 minus X. And this, what is that? Well, we know that this is 2 meters. 2 meters. So this is X minus 2. And here again, so this is for question B. We find the moments clockwise, the clockwise moments. So the clockwise moment is 360 times X minus 2. That's the moment of the plank, plus the moment, this is the plank, and this is Jill. So this is the plank, and this is Jill. So this is 360 times X. And the moment of the anti-clockwise moment is the moment of Jack. So it's 480 times 2 minus X. 4 minus X, sorry. 4 minus X for Jack, of course. Jack. And then we equate them. So 360 times X minus 2 plus 360 times X equals 480 times 4 minus X. And we do 360X minus 720 plus 360X equals 480 times 4, 1920 minus 480X. So 720 minus 480, 240. 240x is equal to 1920 plus 20, 2640 divided by 240. That doesn't make any sense. Where did I go wrong? Oh, of course. 720 plus 480, 1200. 2640 divided by 1200. That's 2.2. X is 2.2 meters. Oh, interesting. It's the same value, which is unsurprising. Okay. Somewhat underwhelming, but yeah, not surprising. Okay, I hope I didn't rush too much. I'll try to go slow for these questions next time. So next week we'll do some more maths, and the week after we'll do some more physics. Okay. So I'll leave you here. Enjoy, and see you next week. Yeah, thank you.